Okay, let's get started. Sorry, I was a minute late. Okay. So last time we talked about the PID, right? So which is a very simple, kind of intuitive way of designing control systems. Okay, so what we saw is you have just a proportional component that is, the temperature is 2 degrees too low, let's increase the heat power, okay? Then we looked at what is the effect of a derivative component, right? So now I'm getting to my steady state too quickly, so slow down a little bit, let's dampen the motion, okay? And so that's something that actually helps with the stability. And we look at the integral component, that is something that allows us to reduce the steady state error, okay, possibly to 0. Now, what we'll do is, okay, thank you. What we'll do today is look at something that kind of is a little bit more systematic way of going through the same process, okay? And that we will also establish some connections between the PID design and what we'll discuss today, okay? So what we do today is something called loop shaping. We will be clear why, because essentially what we want to do is we have the loop transfer function, okay, on the body plot, okay? Remember that we said that typically on the body plot, the way that you represent the specification on the body plot is a bunch of obstacles on the left, right? So those are the obstacles these are the specification about command tracking, distributed rejection, okay? So you have obstacles on the left, you have obstacles on the right that corresponds to noise rejection. And then essentially what you want to do is take your loop transfer function and literally bend it, okay? And steer it in such a way that avoids all those obstacles. You may not believe it, but this is all there is to it, okay? For me, when I was studying this stuff, even before I started understanding what I was doing, so don't panic, follow the rules. Even at the stage where I was just following the rules, at the end of the day, what becomes is take the loop transfer function and say, well, here I'm turning it down a little bit, here I'm turning it up, so it's kind of like a pipe bending, okay? So it's plumbing, okay? And so this is what we will do today, okay? Before we get into that, I will just want to recap some of the things that we said actually 2 weeks ago. Grown-ups, people who are no longer amateurs in the control design, they typically like to work with frequency domain specifications because these are really the specifications that allow you to separate between things like, on one hand, you want your control system, of course, to be stable, but you want your control system to follow commands, right, quickly, okay? But also you want your control system to be robust. You want your control system not to be sensitive to noise, okay? How do you distinguish between what is a command and what is noise? Commands are a low frequency, noise is high frequency. Okay, so unless you get into the habit of thinking the frequency domain, it's very difficult to make this distinction. Okay, so and typically, as we said, commands and disturbances are something that act at low frequencies in order of, 1 hertz, 10 hertz, but not much more than that. Right. So what we said is that the human brains work at about 10 hertz. So. No point in going much faster than that. Noise, on the other hand, is something that is typically a high frequency phenomenon, right? So 100 hertz, kilohertz, or more. Okay? So, and we can reconcile both command tracking, distributed rejection, and noise rejection by separating these things frequency-wise, okay? So what we want to do is make sure that the closed loop transfer function is about 1, okay, at low frequencies. The closed loop transfer function being 1, what it means is that the output is exactly the same as the input, okay? So you want the output to match the input at low frequencies. Great, fantastic. On the other hand, you don't want the output to match the input at high frequencies, because what you know is that everything that you see in the input at high frequency is garbage, okay? So in fact, what you want is the magnitude of this transfer function at high frequencies essentially to be as close to 0 as possible, okay? We cannot make it 0, so what we will say is just make it much smaller than 1, okay? So, good. So how do we write this thing? How do these things get turned into these obstacles, right? So this is stuff that we did 2 weeks ago, okay? So I'm just reviewing that, right? So essentially what I want the sensitivity for good command tracking. I want the sensitivity, which is 1 over 1 plus L of j omega, to be small, okay? That means in order for this to be small, I need the magnitude of L to be large, right? So I want the magnitude of L to be large, and typically what we do is we just say, sensitivity times some weighting function W1. I want this to be less than 1. You do the algebra. What you get is that L of j omega must be larger than some function at low frequencies. Okay, this is the low frequency obstacle. Same reasoning for noise rejection. Now we want the closed loop transfer function T, the complementary sensitivity T, to be small at high frequency. In order for this to be small, what you need is L of j omega, the magnitude has to be small. Okay? So then again, what this translates to is L of j omega must be less than some function W2. Okay? This is the high frequency obstacle. Okay? Last, an additional specification you can have is a specification of closed loop bandwidth. Okay? So essentially what we say is that we want our response, our output, to match the input up to a magnitude factor, of 0.7. Okay, so essentially we want the magnitude of the output to be at least 70% roughly of the magnitude of the input. Okay, where do you get this point? This actually turns out to be exactly essentially. So if you want to say that you want your output to track the input up to 70%, up to say 10 hertz, then what this translates to is that actually you want the crossover frequency to be 10 hertz, okay, on the body plot. And this is what we got, at the time, 2 weeks ago. So essentially what you want is you have this bad area, this low frequency obstacle. You want to be above it. You want to be below the high frequency obstacle, okay? You want to cross the 0 dB line somewhere at the frequency corresponds to the bandwidth, to the closed loop bandwidth that you want, okay? For robustness, you want to cross this line with an angle that is not too steep, okay? So typically what we want to have is something that is close to be about 20 dB per decade, okay? And that's all there is to it, okay? Really. So how do we do that? We have a number of tools at our disposal, okay? The first one is, as in PID control, is proportional compensation, okay? So proportional compensation, what is the effect of proportional gain on the body plot? The effect is just to shift the magnitude plot up and down, okay? I increase the gain, I move the whole body plot up, okay? The magnitude plot. What happens to the phase plot? Nothing, okay? Okay? Good. So, but just moving the body plot up and down may not be sufficient, right? Because maybe I clear the low frequency obstacle, but then I'm too sensitive to noise, okay? So what I want to do is not only move it up and down, but also bend, shape this loop transfer function. The way we do it is by using what is called dynamic compensation, okay? So we choose a controller, which in this case is also called a compensator, which is not a static dynamical system. So it's not just a gain, okay? So now it's something that actually has a transfer function, and we write this transfer function C of S. How do we design this transfer function? Essentially, we just mix and match one or more of these basic elements, where the basic elements are a gain k, okay? Something that's called the lead, okay? So essentially then we will look at this, kind of like a simple fractions where you have a first order polynomial on the numerator and the first order polynomial on the denominator, okay? So you see that this fraction here is the same as this fraction here, okay? But this is something that is called a lead if essentially you see that, where is the zero in this transfer function? The zero is at a, right? What is the value of s that makes the numerator zero? It's actually minus a, okay? So the zero is at minus a, the pole is at minus b, so if the zero occurs before the pole, then this is something that's called the lead, okay? We'll see why. If the pole occurs before the zero, then this is called the lag, okay? And what we'll do is we'll just put together 1, 2, 3, or more of these factors to get our compensator, okay? Questions? So these are the building blocks, okay? So what are the effects of proportional control? As we said before, if you just multiply your transfer function, your loop transfer function by k, then the only effect is to move the magnitude plot up, okay? Up or down. The phase plot is not affected. If the system is open loop stable, then we know that for k goes to 0, for small enough k, then the closed loop will also be stable, okay? Because essentially, if I set the gain to 0, is essentially the open loop behavior. Okay. However, we may not be able to meet other constraints. For example, the command tracking or or noise rejection or crossover or bandwidth without compromising stability. Okay, so proportional control may not be sufficient. So one of the things that you can do is use this lead compensator. Okay, so lead compensator is essentially, if you think about it, is look at it written this way, okay? What do you think that this looks like if A gets closer to 0, if A gets smaller and smaller? Okay, so B is larger than A, right? So then what you have is A is very small, and let's say B is very large. What does this look like? If A were to be 0, what is the numerator? Come on. If A were to be 0, the numerator would be just S, right? And then there is a gain right in the front. We don't care about that, right? If the numerator is S, what is that? What is S? Just a factor of S in the transfer function. Anybody? Yeah? Exactly, right? So when A gets closer to 0 and B remains large, okay? So then this is something that will approximate a derivative, okay? So the lead compensator has the following main effects on the frequency response. Actually, let's look at what the body plot of the lead compensator is, okay? Remember that what we have is a 0. Let's write it here, right? So in this case, we will have, say, a 0 here, right? And then we have a pole, right? So this will be A, and this will be B. The frequency will be A and B, and we know that A is smaller than B. A comes first, so the 0 comes first, so you go up in the magnitude plot first, and then you go down, that is, you go horizontal again, okay? So this is the effect. This is how your loop transfer function will be reshaped, okay? So nothing happens up to the frequency A, then the slope gets moved up by 20 dB per decade, and then down again and goes flat, okay? What happens to the phase? You see that the phase starts at 0. Then, around A, you start feeling the effect of the 0, and then you have the increase in the phase, okay? This ideally would like to go all the way to 90 degrees, okay? But then you start feeling the effect of the pole, okay? And then the phase goes back to 0, okay? Now, where is the maximum? So you see why this is called the phase lead, right? Because this compensator is called the lead because you see that there is a phase lead. So the net effect on the phase is a positive effect, okay? Where is the maximum phase lead? Is actually here, right? What is this frequency? How would you describe it? In simple words. Right, so it's kind of like, it's the mean of the two frequencies of the pole and the 0 on the logarithmic scale. What do you call that thing? It's actually the geometric mean, okay? So this is the geometric mean. This is square root of AB, okay? Which you can verify is exactly, 1/2 the sum of these two when you consider the logarithms, right? So the sum becomes the product, 1/2 becomes square root, okay? So it's exactly the same thing on the logarithmic scale, okay? So this is called the geometric mean, right? And corresponds to just the midpoint on the logarithmic scale. Now, something that you can imagine is that the maximum phase lead that you have, at this point, it depends on how far, so it occurs at geometric mean, right? But also depends on how far A and B are, right? For example, if I had A here and B here, right? So what would the, I don't want to make this too complicated. But let's try to do it, okay, with a different color, okay? So let's say that now I have another compensator where the 0 is here and the pole is here, okay? So I'm keeping the geometric mean at the same point, okay? What do you think that the magnitude plot will look like? The magnitude plot will kind of be flat up until when I get to the 0, right? Then it will go up by 20 dB per decade, up to the frequency of the pole, where it will be flat again, okay? So in fact, if you look at it, the total magnification that you have for large high frequencies is actually given by B over A, okay? The ratio of the pole over the 0, the frequency of the pole over the frequency of the 0 gives you by how much your transfer function will be amplified at high frequencies, okay? What will happen to the, to the phase plot? Well, what you have is that, okay, so the phase will be kind of like it's 0 up to here. At this point, will start increasing, right? But then you start feeling the effect of the pole much earlier. So the frequency will, the phase will look something like that, okay? So what you see is that as you bring the pole and the 0 closer, the net lead that you get is getting smaller, okay? What is the maximum phase lead that you could ever get by keeping the pole and 0 very far away from one another? Yeah. 90 degrees, that's correct, okay? Okay? Because, if the 0 and the pole were to be very far, then the phase contribution from the 0 will eventually get to positive 90, right? And then eventually you will feel the effect of the pole and go back to 0, okay? But it will never be more than 90, okay? So keep this figure in mind, and let's try to think of what happens to your response, right? So essentially what we are doing is we are increasing the magnitude at high frequencies. By how much? By the ratio of the pole over the 0, okay? We're increasing by B over A. The magnitude at low frequencies is not affected at all, okay? So we are increasing the slope of the magnitude at frequencies between A and B by 20 dB per decade, right? So we are putting it one notch up, right? So in the positive direction, okay? The main thing is really that we are increasing the phase around square root of AB. So that is, we are increasing the phase, we are providing a phase lead around the geometric mean of the pole and the zero, okay? So, and clearly, as I said before, the lead compensator approximates a PD controller, okay? As you make A go to zero, okay? This is what we said before. So how do you think that you will actually use a lead compensator? What do you think that the lead compensator is useful for? Anybody?
To keep the phase above 100 - 180 degrees.
That's exactly correct, right? So remember that what we want is that a crossover, you want the phase to be less negative, so we want above negative 180 degrees, right? And in particular, the difference between your phase and minus 180 is what is called your phase margin, right? Which is a measure of robustness, right? So if you find yourself that your phase drops below negative 180 degrees too quickly, too soon, okay? Or maybe it gets too close to negative 180 degrees for comfort, then you want to provide some phase lead, and that's exactly how you provide it, by using a lead compensator. So the main point of a lead compensator is to make sure that you have enough phase lead at crossover, okay? Why did I write this? No, sorry, this is wrong. This is the phase margin, okay? So the typical use of a lead compensator is to increase the phase margin, right? And how do you do it? You essentially pick, you put the geometric mean of your lead compensator at the crossover frequency, okay? That's how you pick the center of the pole and zero. Then how far do you choose them? You know that the farther away you pick them, the more of a phase lead you will have. So essentially what you can do is decide, okay, so this is the crossover, this is the phase margin that I have, the phase margin that I want is such and such, so I will choose to separate this pole and zero by as much as I need to give me the phase lead that I need, that I want, okay? And then you may want, as you do that, you're also, since you are moving the magnitude plot a little bit, you're also shifting the crossover to the right a little bit, so you may want to reduce the gain also to maintain crossover where you want it, okay? What are the side effects of a lead compensator? Remember that you are increasing the magnitude at high frequency, meaning that you can increase your sensitivity to noise, okay? So these are the side effect of a lead compensator is essentially increased noise sensitivity, which is the same as we found with a PD controller, right? So what we said with the PD controller is great. It increases your robustness, that is the phase margin, right? But it may make your system more sensitive to high frequency noise, yeah.
Why do you want to pick the crossover frequency?
Where do you measure the phase margin? Right. So you measure the phase margin at crossover, right? So if you want the most bang for the buck, where do you put the maximum phase lead? You put it at crossover, period, okay? Clear? Example, right? So let's say that we have this plant, okay? So this is two stable zeros, two stable poles at square root of 2, okay? What I want is, I want a bandwidth of 5 radians per second, and I want a phase margin to be at least 45 degrees, okay? So the original transfer function is the blue one, okay? So as you see, this is actually a fairly slow system, right? Right, so, essentially this doesn't give me the desired bandwidth. As you see, actually, you never cross over, right? So, so the bandwidth will actually be very slow. I want the bandwidth to be 5 radians per second, so what I can do is, well, if I shift the whole thing up by increasing the proportional gain, right, I can get this whole thing to be essentially, I can make sure that, what is 5? So it's 1, 2, 3, 4, 5, right? So 5 will be here. So I can just increase the gain by as much as I need to get the crossover at this point, okay? But then what is the phase at frequency 5? 1, 2, 3, 4, 5. You see that the phase is, what is it? Minus 150, minus 160, I don't know, right? So you see that the phase margin is not what we want. Okay, so how do we do it? So essentially what we will do is, okay, so we want the bandwidth to be 5 radians per second. So we will choose as our, the midpoint for our lead compensator to be around 5, okay? By how much do I need to increase the phase margin? Well, let's say that I need, say, 30 degrees more, something like that, okay? 30 degrees is less than 90, right? So I don't need to separate the pole and zero that much. I may want to keep them, like close by. And, if you do it on MATLAB or anything else, what you'll find is that, it's just fine to have this at, essentially have the zero at 1/2 the crossover, right? So the zero will be at 2.5 and have the pole at twice the crossover, which is 10, okay? Okay, and this is exactly what you get, right? So I put a zero at 2.5, the pole at 10, and then I adjusted the gain in such a way that the crossover was actually where I wanted to be, okay? And as you see, the yellow is actually the body plot of my compensator. And as you see, it provides a phase lead of about 30, 40 degrees at exactly where I want it to be, okay? And the red line is actually the loop transfer function of the combined plant multiplied by the compensator, okay? So it may not be readily apparent to you what is happening on the plot. Let's sketch the asymptotic body plot, okay? The asymptotic body plot will be, for the original transfer function, is something like that, right? Up to square root of 2 over 2, up to 0. Actually to square root of 2, right? And then goes down by negative 40 dB per decade, okay? It's a second order system, okay? And as you see, what I have is, the phase will be 0, and then goes down to negative 180, okay? What is the effect of the, of now having this lead compensator? Essentially, what is happening is the following. Well, I'm increasing the whole thing, okay, by this proportional gain, 52, okay? Actually, yeah, this is written in the root locus form, so actually the proportional gain depends on if you think of it as a body gain or root locus gain, so this is written as the root locus gain. Anyway, so then, the transfer function will go down as, will just be parallel to the original transfer function, right? With the difference that at 2.5, there is the 0, so we'll flatten out a little bit, and then at frequency 10, we'll go down again parallel to the original, to the plant transfer function, okay? So you see that what I drew here by hand, okay, just by looking at changing the slope, matches very nicely what I would get from MATLAB. Okay? And this is the power of this method. You know, just with a piece of paper, pencil, maybe a ruler, right? You can actually get a very nice design. You don't need MATLAB for this. Okay? You want to tweak things and make things precise, then you go to MATLAB. But first do it on paper, okay? So that you know what the controller should look like, and then you use MATLAB, yeah? Oh, okay. Yeah, good point. So what I know is that I want their geometric average to be 5, right? Geometric. Oh, he was asking, thank you for reminding me. He was asking how did they choose the numbers 2.5 and 10? Okay, so the point is that I want their geometric mean to be 5. Okay, so what it means is that by how much do I need to multiply? What's happening?
It's okay. Sorry, we have a microphone here. So
Oh, yeah. Okay. Yeah, thank you. So where was I? So essentially, you know, one way that you can look at it is I know that the geometric mean must be 5. So I just need to multiply 5 by some number, let's say 2, and divide 5 by the same number, 2, to get the pollen 0. I can choose that number to be 10, I can choose the number to be 20, or I can choose the number to be smaller. So keep in mind that the smaller it is, the less of a phase lead I will get. The larger it is, the closer to 90 I will get. Okay, in this case, do I need this pollen 0 to be that much separated? Not really, because I don't need 90 degrees of phase lead. 30 degrees will be fine. Okay? And this is something that you will get, actually you can get it from just drawing, drawing the, what is called, this body plot, right? Just look at this. So keep in mind that, so this would be the body plot of the body phase plot of the compensator, right? And, you can think of this as something that is just, let's draw it in, okay, let's use this yellowish kind of thing. Okay, so think of it as, so this would be something that is essentially starts at 0, will be 45 at the, when you see the effect of the 0, right? So we'll start increasing something like that, right? But then you will start seeing the effect of the pole, right? And it will be, yeah. So essentially what you would have is something that is, something, I don't know, well, there's a little bit, oh, sorry. So here you will start seeing the effect of the, of the pole, so it will be something like that, and then we'll go down, right? Okay? And as you see, so here you can get a sense of how much your phase will increase, depending on how close the two are, right? Okay, so essentially, yeah. You can get a sense of how this is just by sketching that body phase plot, okay? Oops, okay. But, again, here you see that, by sketching it, you actually do get a good sense even with a simple sketch, okay? But this is the kind of thing that, if you want to get precise, then you will go to MATLAB, right? And MATLAB will allow you to figure out exactly what is the exact spacing between the pole and 0, okay? But the point is, I choose 5 to be the geometric mean, multiply by 2, divide by 2, I get the pole and 0 location, okay? Or multiply by 5, divide by 5. Typically, when you want to overdo things, separate well and get almost 90 degrees of phase margin, you multiply by 10 and divide by 10, okay? And you don't go wrong with that, okay? If you want to be a little bit more precise, you can reduce those multipliers, Okay? Clear? We'll do more examples, and you will do more examples. This will become more familiar. Okay? Let's look at the other thing. So this is the lag compensator. So the lag compensator is exactly the same, formally. The only difference is that the frequency of the pole is lower than the frequency of the zero. Okay? So what does a lag compensator look like? Well, it's very similar to what we saw before, with the difference that, okay, so now I have a pole here and the zero here. Okay, so now the asymptotic plot will be straight up until the frequency of the pole, then goes down by 20 dB per decade, and then flattens out. Okay. What happens to the phase? What you see is that now instead of having a phase lead, what we get is a phase lag. Okay. Now you may start asking, why the heck do I want a phase lag? Phase lag is bad, right? Yeah, but on the other hand, what you see is that you can see this as, if you consider this as 1, you can think of this as a big boost to your low frequency magnitude. What does a low frequency magnitude do for you? It reduces the steady state errors. Okay, this is exact. So go back to this. A lag compensator, what it does is decreases the magnitude at high frequencies, okay, which you can see that either something that will increase your or reduce your sensitivity to noise, or something that if you just bring up the high frequency gain to 1 is increasing your magnitude at low frequencies. Okay, is decreasing the slope of the magnitude, meaning that it essentially decreasing the phase around the geometric mean of the pole and zero, okay, by up to 90 degrees. Notice that a lag compensator approximates a PI controller as the frequency of the pole gets closer and closer to 0, right? So if B is 0 here, you get an integrator, okay? How do you use it? Essentially, the point of using lag compensator is to improve command tracking or disturbance rejection, right? Because essentially what you do is you're increasing the magnitude at low frequencies. Okay, so how do you use it? Well, by what ratio you're actually increasing the low frequency gain? Is again by the ratio of A over B, or B over A. Yeah, I think it's yeah, okay, A over B. So just pick what is the gain at low frequencies for this? Or the ratio of the gain at low frequencies versus the gain at high frequencies? If this is 1, then as S goes to infinity, what is the value of the transfer function? If F goes to infinity, the ratio of these two goes to 1, right? So then the your gain at high magnitude is B over A, right? So this is B over A, right? So if I wanted to make this one, essentially what I'm doing, I'm increasing the gain at low magnitude by A over B. Okay, do you follow me? Sorry, I was a little bit confused. Okay. But anyway, so what you do is, since you're using this to increase the low gain magnitude, then just say, I want to increase my low gain magnitude by a factor of 20, okay? Then what I will do is, I will just say that the ratio of A over B must be at least 20. Okay, so this is the boost that I want at low frequencies. Now, what you want to do is, remember that the increase in the magnitude at low frequency comes with the cost of a reduced phase, of a phase lag. Where is it that you absolutely don't want to have any phase lag? Anybody?
You're reaching 180 degrees.
Exactly. So you see where you are actually when you are crossing over, right? So how can I say? Your phase can be as small as you want, right? As long as your magnitude is not 1, right? So essentially what you want to do is make sure that the phase lag occurs away from crossover, okay? So how do you make sure that this occurs away from crossover? You just make sure that crossover is somewhere over here, okay? So that, yes, you do have a phase lag, but it occurs at a range of frequencies where the phase doesn't matter because it's away from crossover. Okay? Question? You want to get the microphone? Oh, that's oh, almost. Yes, yes, you can do that. You can add more poles, to do exactly that. But essentially, the point is that you don't want to have, this big phase lag away from crossover. Okay, just either on the left or on the right, not at crossover. Okay. Oh man, good. Okay. So, lag compensation example. Let's say that I have this plant. Okay, this plant, whatever. Actually, this is what I had before, right? This was my transfer function before with the lead compensator. Okay. Now, what I want to have is I had the previous specifications. Okay, so I want the crossover to be at 5. I wanted to have, what was the other thing? The phase margin to be 45 degrees, right? But now, on top of that, I want to have the steady state error to a unit step to be less than 1%. I don't want it to be 0, so I don't need an integrator, okay? But I want it to be less than 1%. What this means is that, so essentially, if I want the magnitude, let me write it here. If I want the magnitude of the error to be if I want the magnitude of the error to be less than 1%, okay, let's keep doing it after the break, okay? Let's keep going. Okay, what we are saying just before the break is that if we want the steady state error to be less than, say, 1%, remember that the steady state error for low frequencies is about 1 over 1 plus L of 0, right? Assuming I can write L of 0, so I have no integrators, okay? Actually, this is actually equal to the magnitude of 1 over 1 plus L of 0, right? And I want this guy to be less than 0.01, right? So I want this guy to be small, which means that, so I want essentially 1 to be less than 0.01 times 1 plus L of 0, which means, if I want 1 plus L of 0 divided by 100, okay, so I can also write this as 100, okay? So if I want 1 plus, okay, so then what this means is that this is magnitude. Assuming that L of 0 has a phase of 0, which is actually the case in this case, what this means is that I want L of 0 to be greater than 99. Okay? So essentially what you're seeing here is that I want my low frequency gain to be larger than 100, essentially, which is 40 dBs, okay? So what I want is my low frequency magnitude to be at least 40 dB or more, okay? And we see that the original transfer function, even the one after we applied the lead compensator, the low frequency gain was less than 20 dB. So it's not sufficient, okay? So here what we want to do is I want to increase the gain on the left, right? But I don't want to touch crossover. I don't want to touch the phase margin that I worked so hard to fix with the lead compensator. Okay, so what do? Well, I know that I need to increase the low frequency by a factor of, well, you know, probably I did the calculations here. It's probably a factor of, what is it, 15, okay? Right? So then what I do is, okay, so I want the pole to be at a frequency that is 15.3 times smaller than the frequency of the zero, okay? Well, where do I put the zero? I know that crossover must be here, right? I want crossover here, so I will put my zero at least one decade to the left, okay? And, you know, and essentially this is, actually put it even further away on the left, right? So I put my, my zero here, okay, at frequency 0.1. And then I put my pole at the frequency that was 0.1 divided by 15.3, which is, well, you know, somewhere around here, okay? Okay? So you see that the asymptotic body plot for the compensator is something that, okay, eventually is 1, right? Starts at, you know, 15.3 or whatever the number is, goes down when it meets the pole, and then flattens out again. What is the effect of this on the body plot of my loop transfer function? Well, you see that the effect from here onwards is nothing, right? Because the magnitude is 1. But I am essentially increasing the gain at low frequencies. Okay? And this would be the, whatever, you know, the body plot for my loop transfer function. Okay? So you see what is happening? You see that I'm not, remember that crossover was here, right? So here you see that the phase, even given the lag compensator, is not changed by much, right? It's just changed by a very small amount, right? And we see that the phase lag is occurring here. The phase lag occurs to the left of crossover. So yeah, we may have a phase lag, who cares, right? Because we are not affecting the phase margin. Okay? Got the point? Yeah? Okay, that's a long throw. Okay, guys, help me out.
At high frequencies, I don't quite understand. Before you said that at high frequencies the magnitude is just decreased by B over A.
Right.
How do we get to a magnitude of 0 here? I didn't.
Just multiply by A over B. So if you multiply the whole thing by A over B, then at high frequency.
So that's our gain at the end.
Right.
Oh, okay.
Right. At frequency you have no effect is 1. But at low frequency you're increasing the magnitude by A over B.
Thanks.
Right. Okay. Clear? So how do we put all these things together? General procedure for open loop stable systems. Okay, so start from the left. From low frequencies to high frequencies. First thing that you need to do is look at the specs and try to figure out how many integrators you need. Okay, if people tell you I want my closed loop to track units, to track step inputs with 0 steady state error. You know that, no matter what you do, you will need to have at least one integrator. Do you already have an integrator in your loop transfer function in your plant? Yes, fine, you're done. No, you have to add an integrator, period. There is no other way around it, okay? So figure out how many integrators are needed and put them in your compensator, okay? Given that, then you will have this command tracking disturbance specification, the body obstacle on the left, the low frequency body obstacle. Increase the gain such that your loop transfer function clears that obstacle. Okay? Easy. Then what you will do is, then you will start inserting forms, terms of the form tau s plus 1, okay? The reason why I put this thing as tau s plus 1, because in this way they do not affect the low frequency gains, okay? And essentially here what you're doing is just steering the loop transfer function in such a way that the body magnitude plot intersects the 0 dB line at the crossover frequency that you want. Also, you make sure that you don't want to cross the 0 dB line too steep. Why? Remember that the slope of the magnitude plot corresponds to the phase, right? And essentially what you want to do is cross the 0 dB line at the crossover frequency that you want, but you want to cross it gently, like with a shallow slope, right? Approximately negative 20 dB per decade. Okay, you don't want to cross it too sharply, because if you cross it too sharply, then your phase will be much lower. It will be negative 180, it will be lower than 180, meaning that you have a closed loop that is unstable, okay? Or you have a very small phase margin, okay? So then just steer the loop transfer function by turning to the right, it is downwards by adding a pole, right? Adding a lag, or to the left, that is upwards by adding a 0, okay? Aim for the crossover and make sure that you cross the 0 dB line at crossover with a shallow slope, okay? Pass the crossover, get to your point, add as many poles as you want to clear the high frequency body obstacle, okay? For example, let's say I have this system with this, a system with this transfer function, okay? Whatever that is, okay? So we have 2 zeros at 10, I mean, the zeros are at negative 10, right? But the frequency is 10, okay? And then I have 1 pole at the origin and 2 complex conjugate poles at, with natural frequency square root of 2, okay? I want to have a feedback control system such that the closed loop is stable. Steady state error to unit step is 0. Commands up to 0.05 radian per second are followed with at most 1% error. Phase margin no less than 40 degrees. Noise at frequencies higher than 100 radian per second is attenuated by at least 40 dBs. Great. Okay, so this is our task. How do we go about it? First of all, this is one of those examples where the open loop is actually stable and minimum phase, meaning that it's okay to use body and that's it. You don't have to worry about night phase, you don't have to worry about other things, okay? So let's just do body, okay? I want the steady state error to unit step to be 0. Do I need to add an integrator in my compensator? Yes or no? I already have one, okay? So I don't need to have an additional integrator. Fine, that part is easy, okay? Now the next thing that it says is that the commands up to 0.05 radian per second are followed with at most 1% error. What does it mean? Where is 0.05 on this plot? Is around around here, right? Okay. So then if I want commands up to that frequency to be followed with at most 1% error. The same calculation as before, what I want is my loop transfer function to have a magnitude of at least 40 dB up to frequency 0.05, okay? So what is this low frequency body obstacle? Something that will look like this, okay? So I had to design my compensator in such a way that the loop transfer function clears this obstacle above, right? What are the other constraints? The phase margin is no less than 40 degrees. Noise at high frequencies attenuated by at least 40 dBs. So what does it mean? For me, high frequencies is 100 radians per second, and I want an attenuation of at least 40 dB. Okay, so then I have this other obstacle on this plot. Okay, and then I need to have I want the phase margin to be at least 40 degrees. So essentially, at crossover, which wherever it will be, I want my phase to be above this line, roughly. Okay. Okay, so what do I do? What would you do? Any ideas for what the good compensator would be for this one? No. Okay.
Firstly, I would add some gain that the low frequency obstacle would be cleared.
Say again? I didn't get it.
I would add some gain that the low frequency obstacle would be cleared.
How much do you think you need for the gain?
Well, 20 in magnitude, but we have
20 what?
20 decibel in magnitude.
dB, but which corresponds to?
10.
10. Yeah. Okay, so multiply everything by 10. What happens if I multiply everything by 10? Well, I'm shifting this plot up, right, by 10. Okay. Oh, by the way, if we were to draw the plot, the asymptotic, body plot, what would it be? So I'm increasing it by 10, with something like that. Then I get to, what is it? So here I have 2 poles, right? And then I have 2 zeros here, if I remember correctly, yeah. Okay, so here I will go down, oh, sorry. Here I will go down, right, by 40 dB per decade, more. And here I will go again to this slope, okay? Good. Okay, what else would you do? So this, this is true that this allows me to clear the low frequency obstacle, right? And also allows me to clear the high frequency obstacle as well. I was already clearing it anyway, and so actually by increasing the gain by 10, I'm not increasing my high frequency, my noise sensitivity too much, okay? So I'm still fine. But what else? Is this a stable closed loop?
So I would add the tau s+1 term.
Yeah, but why? So for example, what can you say about the closed loop stability? Is this system closed loop stable? Yeah.
No, it's not closed loop stable because at crossover we have more than minus 180 phase.
So crossover is here, right? This is the frequency at which we hit the 0 dB line. And, well, I mean, it's, what is it? It's around here. Well, I think that, technically it is stable, but you see that the phase margin is what? 3 degrees or something. You don't want that. Okay? So how do we fix that?
Yeah, we could use a lead compensator.
Right? How would you choose this lead compensator?
Yeah, A times B square root needs to be 60.
To be where? The square root of AB, of A times B?
So both the pole and the zero we use, the square root of those. And we need to shift up the phase by 40. So.
Okay. Okay, fine. So what we need is, we need to center this pole in zero, let's say around this point, right? So, and what is this point? It's probably, let's say 2 radians per second, roughly. Okay. How would you choose this? The pole in zero? So they must be centered at 2, right? So let's say multiply by 5 and divide by 5. Maybe enough, maybe not, right? So, so then essentially we can choose a lead compensator where we have a, let's put it in, so 2 divided by 5 is what, 0.4, right? So we'll be somewhere here. So we're putting a 0 here, and 2 multiplied by 5 is 10, right? So essentially, okay, so then we are putting a pole here. Okay? Fine, so then what will happen is that, now here at this point, we will go a little bit flatter, right? At this point, we'll start going down again. And here at this point, actually, our slope will be the same one, okay? Good. What happens, so now as you see, it may be the case that our crossover frequency has increased a little bit, right? So now the crossover is not exactly at 2, or it's not where it was before. Now the new crossover will be moved a little bit to the right, will be moved to this point here, okay? One thing that we could do is to keep crossover where it was before. I could reduce the gain, but then if I reduce the gain, I'm no longer meeting the obstacle, clearing the obstacle on the left, right? That said, it may be the case. So what happens to the phase? The phase will be, at this point, will be 45 degrees, more positive, right? So essentially the phase will be something like, my maximum phase gain will be around here, right? So my phase may be something like that, right? Or whatever, that looks like, okay? It may be the case that exactly at this point, the new crossover, it may be the case that my phase margin is sufficient, okay? What happens to the high frequency noise sensitivity? Still, if I've done my body plot correctly, I'm still clearing this obstacle, okay? Given this new lead compensator. So, this very quick, back of the envelope or back of the iPad kind of design, essentially what we are saying is that, this is S S over 0.4 plus 1 over S over 5 plus 1. This compensator here should allow us to meet all of our specifications, okay? Making the system stable, the closed loop system stable, reducing the steady state error to something that we want, and not making the system too sensitive to high frequency noise. Yeah, question? No, you see, again, this is a little bit, it's easier for you to do it if you have like some square paper or something like it or something, right? But look at, now the new crossover frequency is this one, right? What is the phase? If I did things correctly, the phase seems to be, it may actually be, above my, so the phase will be around here, let's say around negative 135, which is more than 40 degrees away from negative 180, okay? So assuming that this sketch is correct, I'm actually done with my design, okay? Okay? But this is where things can get a little bit iterative, okay? Because here what we found is that, okay, by adding the lead, we are also moving the crossover a little bit to the right, okay? So the maximum phase lead is not occurring at 2, is not occurring where I want it to be, right? It's occurring a little bit at higher frequencies, okay? One thing that you can do if you want to keep the crossover frequency fixed is to lower the gain. But by lowering the gain, we will not meet the obstacle on the left, right? And this is where a little bit of the art comes in, okay? So then you just choose how you want to steer the loose transfer function, and you just do that by adding poles that steer it down, adding zeros that steer it back up, okay? There are many solutions, okay? Most of them will be fine. Typically, what you want is meet all of your specification with the smallest possible number of additions, right, of new poles and zeros. Okay, so more elegant design. But, there are many solutions to this problem. Okay? We will do more and more of this, okay? But at the end of the day, it's all about taking your loop transfer function, moving it up, and then bending this pipe in such a way that it clears all the obstacles, okay? Now, something else that I want to say is that, why does this PID structure work so well? Keep in mind that the form of an implementable PID is something that actually looks like that, right? So we need to have a second order polynomial at the numerator, right? Because we have one coefficient that multiplies S squared, one coefficient multiplies S, one coefficient multiplies, just a constant term divided by S. Remember that in order for this controller to be implementable, what I want is that I need to have at least as many poles as I have zeros. Since I have 2 zeros, I need to have at least 2 poles. One is at the origin, that's the integrator. Then I need another pole, which I will put at some high frequency, okay, just to make the transfer function causal. Okay? This is the factor form of a PID controller, okay? I'm just writing it as factors. But now you can group things in this way, and then what you see is that K, okay, is your proportional gain. Then you can group the first zero with the pole at the origin, and write this as S plus 0. And you see that this is essentially something where the pole occurs first and then the 0. You can think of this as a lead, right? An extreme form of a lead where the pole is actually frequency 0. Sorry, a lag. Sorry, I wrote it correctly. So this is a lag, right? So the pole occurs first. And then you have these other terms where now I have a 0, and I have a very high frequency pole, and this is a lead. Okay? So you see that the PID is actually something that can be thought of as a lead lag compensator. Lead lag compensator is something more sophisticated, a little bit more general, but includes the PID as a special case. Okay, so these are not two different things. Clear? Okay. Okay, now things get a little bit fun. Now, something that I always insist on is the following, that yes, it's fine to do all of your design on the body plot and look at closed loop stability, phase margin, gain margin on the body plot, as long as your system does not have any poles or zeros in the right half plane, okay? Meaning that as long as your open loop system is stable and it is minimum phase, then it's fine to use body. Unfortunately, that's not always the case. Very often you will be faced with the task of stabilizing a system that has open loop unstable poles or has no minimum phase zeros. What do you do in that case? Go back to your boss and say, well, I cannot do that. No, you can say that, right? So, well, you need to figure out something. So the guaranteed correct way of approaching that is do your design as much as you can on the Nyquist plot, on the root locus, any tool that actually gives you correct answers when you have unstable poles or no minimum phase zeros, okay? If you want to use the body plot, for example, to address things like comment tracking, noise rejection, things like that, you can still do it, okay? It's a little bit more complicated. But let me tell you about one possible way of doing it. Something that you can do is take your transfer function, P, and rewrite it in a slightly different way, okay? So what I say is, just factor it this way. What you will have is this PMP, this stands for the minimum phase version of P, okay? PMP is you obtain from P of S, replacing all the unstable poles with their mirror image on the left hand half plane, and replacing all the no minimum phase zeros with their mirror image in the left half plane. Can you do that? Well, not quite, right? So then what you will have to do is multiply by another function that we will call d of s. And this is a d of s that, this is the transfer function that contains all of the poles and zeros of P in the right half plane, right? And all the new things that you replace them for, but of course you have to divide by that in a sense, right? So, I have this example, right? Let's say the P of S is S minus Z and S minus P over S minus P, where Z and P are positive numbers, meaning that now you have a no minimum phase zero and you have an unstable pole. How do I put it in this form? Well, I would just say the minimum phase version of P is S plus Z over S plus P. You see what I'm doing? Right? So I'm just moving the zero from Z to negative Z, and then moving the pole P from P to negative P. Of course, in order for this to work, what I need to do is I need to multiply by this function d of s, such that this will cancel with this will cancel with this, and then what I'm left with is exactly my original transfer function, okay? So I'm just rearranging things, okay? How is this useful? Think about this transfer function here. This transfer function has one special property, okay? And let's try to draw it, okay? Let's try to understand it geometrically. Let's assume that d of s is, say, s plus z over s minus z. let me write it as this, okay? Okay. What is this transfer function? What is the magnitude of this transfer function? So what is the magnitude of d of s? For s is equal to j omega, right? So remember that what I want to do is compute d of j omega, right? Which is j omega plus z minus j omega plus z. Okay, this is j omega. And let's say that this is minus z, and this is z. Okay? What is the magnitude of this transfer function? The magnitude of this transfer function will be, what is the magnitude of the numerator? The magnitude of the numerator is the distance between the 0 and my j omega point. Okay? What is the magnitude of the denominator? That's the distance from my pole to the j omega point. What is the magnitude of the ratio? Is 1 divided by the other, which is 1. Okay? So you see that the magnitude of this thing is actually always equal to 1. Okay? Whenever you see something that has this form, where you have these terms of, s plus z over s minus z, s plus p over s minus p, that's actually something that's called an all-pass filter, because it's a filter that has magnitude 1 for all frequencies. Okay? On the other hand, what is the phase of this thing? The phase of this will be, is the phase of the numerator, which is this angle here, right? Minus the phase of the denominator, which is this angle here. Okay? So you see that, so this would be, say 45 degrees minus, say, 135 degrees. So this would be, at this point, would be negative 180 or something, right? No, sorry, negative 90. Okay? Anyway, so if you look at the body plot for these things, what we will have is something that looks like, the magnitude is just flat at 1. And the phase is something that, you can set it in such a way that it's always negative. And, we'll have some just phase contribution, okay? So one way of thinking of this is, now let's pretend that I'm just trying to stabilize a nice plant that is given by the minimum phase transfer function, okay? And the body plot, the magnitude body plot will look the same, okay? Because the magnitude body plot of D is just 1, right, 0 dB. However, what I call this little body demon is actually putting D of S in your control system. And D of S is something that doesn't change the magnitude plot, but introduces a phase lag in your phase plot, okay? So D of S does not alter the magnitude plot, but messes up its phase plot, okay? And in particular, by introducing a possibly massive phase lag. So what does it look like? So, okay, now what we have is a stable open loop plant, but with a no minimum phase 0, okay? So what I will do is I can write this as, what is it? I have my original transfer function, I have the minimum phase version of it, and my pen is dead. Okay, so I just use my fingers. Okay, so you see that the magnitude plot is not affected, okay? But look at, so the magnitude plot for my original transfer function is, what is it? Is the yellow line, the phase plot for my nice transfer function is the blue one. So you see that that I may be led to believe, if I just look at the minimum phase one, that the maximum phase lag is actually negative 190 degrees. But you see that once I take into account the effect of this body demon, what I have is actually an additional phase lag of another 180 degrees. Okay, so just look at the overall phase plot, which is given by this yellow line. This is 360 degrees, so think of that as 0. Okay, you see the okay, and what you will see is that the effect of this non-minimum phase 0 is actually to bring the phase to actually be negative 270. Big problem. Okay, so what do you need to do to make sure that your closed loop system is not unstable? You see that the phase drops below negative 180 degrees at the frequency of, say, 20 radians per second. Okay? So what that means is that actually your crossover, you cannot push your crossover to be very high because you will be unstable, right? So essentially your non-minimum phase 0 limits the crossover frequency that you can use, okay? Because you will see that the phase actually drops below 0, below negative 180 for high frequencies, okay? This is just the contribution of the non-minimum phase 0. Conversely, what happens when I have an open loop unstable system? Do exactly the same thing. What you will see is that now the contribution of my body daemon is to give me a massive phase lag at low frequencies. You see that at low frequencies, the red line, that is my D of S, has a phase of negative 180. Okay? Right, so I thought that for the nice plant, my phase at low frequency will be 0. Instead, I have negative 180. So technically, I'm not unstable, but I have a very low stability margin, very low phase margin. So how do we make sure that the stability margin is large enough? Well, actually, here is kind of like a tough problem, right? So I can only bring the phase margin to be, 20 degrees of something. And in order to do that, I had to choose a crossover frequency that is actually large enough that the effect of my body daemon is not too large, okay? So typically what you have when you have unstable open loop unstable poles, it means that your control system, your crossover must be actually large enough now, because essentially your control system must be faster than the unstable pole. If you have, for example, sometimes some fighter planes, for example, are designed to be open loop unstable. Why do you want them to be open loop unstable? Because now they maneuver on a dime, right? But in order to stabilize those airplanes, do you think that a very slow computer, for example, like a human, or a slow computer would be enough? No. You need to have a fast computer actually stabilizing those systems, because if the airplane just flips and goes unstable, in a fraction of a second, you want your computer to be able to counteract that faster, okay? So, no minimum phase zeros limit how quickly you can move. Open loop unstable poles force you to move fast, okay? If you have both, you're in trouble, okay? But that's where, things get interesting, okay? So, let's summarize what we did today. Okay, so we revisited, how we write the specifications on the body plot, okay? And then we introduced this idea of loop shaping for control design, and this is a technique that you use very well on the body plot, okay? Loop shaping just means take your loop transfer function, move it, raise it or lower it, bend it to the right, to the left, however you need to, in order to clear the obstacle on the left, clear the obstacle on the right, cross the 0 dB line in some place, and cross it with a shallow slope. That's all there is. Okay? Of course, it needs a little bit of practice to do it nicely. Probably your first design will be 5 zeros and 5 poles, right? Like a lot of corrections. And then as you get better, you will learn how to do it in a more elegant way with the minimum amount of corrections that you need, okay? Essentially, you use the standard elements such as gain. The gain is shift the whole thing up. Given the usual shape of the body plot, that means reducing the steady state error, but also increasing the crossover frequency, okay? Use the lead, increase the phase margin, and usually you center the lead at the crossover, because that's where you want the phase lead, okay? Lag, decrease the steady state error. The way you do it is just make sure that you put the 0 of the phase lag to the left of crossover, and then put the pole sufficiently far away that you get however big of a boost you want at low frequencies, okay? You can do that or just do it by hand by steering to the left and right the loop transfer function, okay? Remember that no minimum phase zeros. Whenever you have no minimum phase zeros, don't trust body, don't trust your instincts. Just do Nyquist on the side, okay? Nyquist or root locus on the side. The effect of no minimum phase zeros is that to limit your crossover frequency. That is the closed loop bandwidth. And conversely, open loop unstable poles require your crossover to be large enough, typically, okay? Meaning your compensator needs to be fast enough. Okay, questions? No? So let's stop here. See you guys next week. Oh, just one thing. Today, my children, they have their Christmas show and song and dance and whatever, so I will have to leave around 4:30. So if you want to come to office hours, try to come early, okay? Sorry about that, but thank you.